Welcome to the podcast. We did a whole bunch of equilibrium stuff, and we're just going to keep driving that train down the road. And the AP exam is within sight. Chapter 14 and 15 is going to be all about acid and base equilibrium. Not only strong acids, which you did in regular chemistry, but also weak acids. We'll have some more Ks, we'll have some more ice tables. It'll all be just fine. This is what you're expected to know out of chapters 14 and 15. This would be a good thing to write down to make sure that you know what you should do. Anytime you have an acid, it has a hydrogen attached. So HA is my acid, just any general acid. And over on the right, it's putting off this hydronium ion, this H3O. You could also say that HA just gives off H+. That's an okay way to do it too. But in this reaction, you got HA combining with water, producing H3O, hydronium ion, and most importantly, that A-. So if it was hydrochloric acid, you'd give off the H3O and a Cl-, a chloride ion. The important thing is that whatever is an acid on the left-hand side becomes a base on the right-hand side. Because an acid is just something that gives up an H, and a base is something that can absorb an H. That's Bronsted-Lowry acid theory. So A- over here could totally absorb an H and go back the other way. So we call things conjugate acid-base pairs. The HA and the A- are conjugate acid-base pairs. The water is acting like a base because it absorbs a hydrogen ion. So the water and the H3O are a conjugate acid-base pair. We can write a K for almost anything. We can also write a K for when an acid gives off a hydrogen ion. Notice we don't include the water. Why is that? Because water is a pure liquid, and we would never include it. But we can write a Ka expression. In pre-AP Chem, we never got real strong into what's a strong acid and what's a weak acid, except to say that strong acids are strong electrolytes. They give off lots and lots of ions. So you just need to know a couple facts about strong acids, and they're here. And the most important one down there is pH is equal to pKa. Why is that? Ka is the concentration of the H3O compared to the concentration of HA. Well, the H3O is all of it. It produces all H3O ion, the hydronium ion. There's zero HA left. So when you have a big number on top and almost zero on the bottom, you get a very, very, very large Ka value. So really, the Ka value is more about the H3O concentration. So we can make the statement that the pH is going to be something like the pKa. Strong acids give off, most people would say, weak bases. Strong acids don't give off weak bases. Strong acids give off totally worthless bases. If we look at this table of Ka values for some pretty strong acids right here, we see our good friend sulfuric acid coming in at 1 times 10 to the third. That means it's 10 to the third away from its original concentration of 1 molar. That's a pretty strong acid. Hydrochloric acid jumps up from 1,000 to 1.3 million. Hydrobromic, stronger still. It's a billion. Hydroiodic, 3.2 times 10 to the ninth, is 3 billion. And one of the strongest acids out there, perchloric, its Ka is so big, all we write is large. But if those are the acids, then what do the bases look like? Their conjugates look like over here. And those conjugates are going to be really, 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 really weak. So much so that those things we're just going to call worthless. They just don't even count. Weak acids, on the other hand, they ionize less than 5% of the time. So they're not going to make a whole lot of ion. So when a weak acid produces a conjugate base, it doesn't produce a strong conjugate base. It produces a relatively strong conjugate base, meaning it's a relatively strong compared to water. Don't say I've got a weak acid, so it makes a totally strong conjugate base. Lie. Total lie. Weak acids make a relatively strong conjugate base, meaning compared to water. We say that water in and of itself is both an acid and a base, and you can tell that the water is giving up a hydrogen and the other water is accepting a hydrogen. So this too is a conjugate acid-base pair. What do we like to do when we see a reaction like this? We like to write a K expression. So what's the K expression for water going to be? Well, we don't include the water, so what's the K expression going to be? You're right. The K expression is just going to be the hydronium ion concentration times the hydroxide ion concentration. And we know that at 25 degrees, the Kw, or the H3O concentration times the OH concentration, is 1 times 10 to the negative 14th. You guys learned in pre-AP Chem that you can take the negative log of the hydrogen ion concentration and give you a value for pH. pH just tells you on a scale of 0 to 14, that's at 25 degrees, 0 would be really acidic and 14 would be really basic. Once again, there's the Kw expression, and we can take the P of it, and the P means the potential of it. The potential means take the negative log of it. So if we take the negative log of 1 times 10 to the negative 14th, we get the answer 14. If we take the negative log of the hydrogen ion concentration, we get pH, and the negative log of the hydroxide ion concentration, we get POH. Where does the plus sign come from? The plus sign comes from the law of logs. Yeah, welcome to Algebra 2 and Pre-Cal. Most all of your life, you know that the pH scale runs from 0 to 14, but that assumes 25 degrees. What happens if the temperature changes? The temperature changing is just like any other kind of equilibrium. Here's the autoionization of water. You'll notice that it takes energy to break those bonds apart. It takes energy to break those waters apart. If we measure the hydrogen ion or the hydronium ion concentration, remember, same thing, at 25 degrees, we get 1 times 10 to the negative 7th molar. That means that not very much H3O ion is being made. The OH is exactly the same amount. And you can tell from the stoichiometry above, you get a 1-to-1 relationship. So however much H3O is made, same amount of OH is going to be made. If we multiply those together, because that's the Kw expression, we get 1 times 10 to the negative 14th. But remember, the reaction is endothermic. Therefore, as you're adding energy to it, the energy is a reactant. So when you add energy, it's going to shift the equilibrium over to the right. More ions are going to be made. So let's see what happens, and we go up from 25 degrees. At 30 degrees, if we measure the H3O concentration, we get 1.21 times 10 to the negative 7th. In other words, a higher concentration of ions. That's because more is being given off. The OH concentration is the same amount. No surprise there. There's still a 1-to-1 relationship. When you multiply the two of them together, what do you get? 1.47 times 10 to the negative 14th. Do me a favor real quick. Get your handy dandy calculator and find the pH of the H3O concentration. Find the POH of the OH concentration. And just for kicks, find the pKw. Because the pKw is what the pH and POH add up to be. I got a pH of 6.917. A POH of 6.917, and when I add the two together, I get 13.834. What does this mean? This means that as the pKw drops, more ions are being made. If the pKw, when they add together, gets smaller, then you know more ions are being made. If you don't believe me, double check your calculator work. What's that? You want to warm it up a little bit more and see what happens? Okay, I got you. At 40 degrees, the hydrogen ion concentration, or hydronium, whichever one you'd rather do, is 1.71 times 10 to the negative 7th. Even higher. The Kw, when you multiply them together, shown here. Stop and go ahead and take the pH, POH, and pKw. See what you get. I got a pH of 6.767, even lower than 7. So the pH is 7 degrees at 25 degrees, and at 40 degrees, it's 6.767. So what was the pKw? The pKw was 13.534. Was 13.534, even lower than it was before. So to sum it up, as temperature increases, Kw increases because more ions are being made. And if temperature decreased, well, the Kw would decrease because less ions are being made. This is how we're going to solve for the pH of a weak acid. The pH of a strong acid ain't no big thing. If you got a 2 molar HCl solution, you take the negative log of 2 molar, because HCl, all of it turns to ions. You got a 0.2 molar solution of nitric acid, you take the negative log of 0.2 molar. It's just so easy. For weak acids, we're going to have to do something different. We're going to have to go ahead and write the equation of it acting like an acid. We're going to write a Ka, an equilibrium expression, build ourselves an ice table just like before. We're going to fill up the ice table. We're going to make the assumption or neglect the X just like we did in class. Then we'll calculate the hydrogen ion concentration in the ice table. And finally, once we know that, we can find pH. Yes. Okay. I'll come up with some kind of sample problem. Ta-da! So we got a weak acid, acetic acid, H, C2H3O2. How do you know it's a weak acid? Look at the value of Ka. Is the Ka greater than 1? No. Is the Ka less than 1? But of course, anytime the Ka is small, you know it's a weak acid. The smaller the value of Ka, the weaker the acid is. Step 1, I'm going to write an equation. There's acetic acid giving off a hydrogen ion. We can go ahead and write a Ka expression for it too. Ka is equal to the concentration of the C2H3O2 times the concentration of hydrogen ion over the HC2H3O2. Let's ice that sucker down. I put in my initial concentration of the acid. The other two start at 0, minus X and plus X, just like we've been doing. I plug it into the Ka expression, the products over the reactants. And since no one likes to solve using the quadratic formula, we are going to neglect the X or say it pretty much doesn't matter. Ka is equal to X squared over 0.5. All I have to do is plug in the numbers. So when I plug in my numbers, I can solve for X, and X in my ice table is my hydrogen ion concentration. Since I know my hydrogen ion concentration is 3 times 10 to the negative third, I'll take the negative log of that, and I'll get a pH of 2.52. If this had been a strong acid, it would have had a pH of 0.3. 0.3 is pretty acidic. This is a weak acid. It doesn't produce as many ions, and it has a pH of 2.52.